Okay, welcome back. Let's get started. Hello. Hello. We're going to have class now. Okay. Today we are talking about, we're still on operating systems, of course. We're talking about I/O systems, mass storage systems, and file management. So it's a pretty quick and easy lecture. Not as technical as some of the other concepts that we've looked at so far, but equally as important in terms of the operating system and the services it's providing. So we're going to look at the concept of the file, so file concept and the structure, directory structures, file organizations, access methods, and the concept of protection. And I believe this is lecture 10. Actually, good question before I start. It is lecture 10. Okay, very good. It is lecture 10, so if you're downloading the slide set, if I go through it too fast, you can download it and go through it at a slower pace if you want. So what are we looking at? We're looking at operating system's functionality. Operating system provides the utility of accessing files, and which is really considered secondary storage. So secondary storage has directories, files, devices, all sorts of different things on it. In terms of the file concept, by its abstraction, it's a continuous logical address space. So the operating system abstracts from the physical properties of its storage, the device itself, and it defines a logical storage unit called the file. So the file is nothing more than some predefined bytes on a secondary drive that's giving us this abstraction. We put all the bytes together and we have this file. And then the operating system maps the files to the physical devices. We need an operating system to actually read the files off of the disk, and the operating system has to have the support for the file format so it knows how to read the particular file structure. So we have different types of files in terms of the concept: data, programs, and documents. The data itself could be numeric, it could be character, binary, it could be stored in any format that might be useful for its data storage. The program itself is the source, it's the object code. It's loading an image essentially into the runtime environment. It's your exe file, usually stored in machine code. And then documents. Everyone is familiar with My Documents from the Windows days. And My Documents is nothing more than an abstraction of documents files that are stored in the hierarchy. In terms of the structure of the file, what we're looking at here is we could have there might be no structure at all, it might just be a sequence of words or bytes that are associated with the file. So we could say this file is called, might have a name or something, and then it's going to be associated to these bytes that come up with the definition of what this file actually is. And then we might have, let's say, for example, a simple record structure that might have lines, fixed length, variable length. Might be a specially formatted file structure called a record. Sort of similar to a database structure in terms of that file. And we might have some more complex structures, formatted documents, relocatable file loads, load files, all sorts of different types like DLL files and object files and all sorts of different types of complex structures. We can simulate the last two with the first method of inserting appropriate control characters. In fact, the file itself, if we're going to format it, we're going to put in characters to tell us what we have. If you've ever actually opened up a Microsoft Word file in a text editor, you can see all the formatting information. There's a header at the top that says it's a Microsoft Word file. There's a bunch of information in there to set the format and other characteristics. So, in terms of how we're going to treat these files and the way the file structure is organized, the question of who decides, well, it's the operating system that decides and also the program. As an example, Microsoft Word decides the format of the Microsoft Word files that it's going to open. That's why there's a header in there, that's why there's information in there to basically help Word figure out, well, what is in this file? What's this data? How's the data supposed to be presented to the user, and how do we work with this file? Well, that's something that Microsoft Word as a program is going to tell you. In terms of file attributes, we have the name, the type, the location, the size, protection, maybe a protection bit, who can read, write, and execute it, the time, the date, the user identification, maybe some information about files are kept in the directory structure, might be maintained on the disk itself, might be in a different index, might be in the FAT sector, might be in all sorts of different locations outside of the file system itself. And to give you a slight example, some of the information is actually stored with the file depending upon the file system structure. And then we have to think, well, what file system structure are you talking about? Well, we have stuff like FAT, which is a file allocation table structure. You know, FAT12, FAT32, different types of FATs. We have different types of Windows files, such as NTFS. We have NTFS Plus, we have HFS Plus, we have HFS, we have all sorts of different, we have Linux extended, extended 2, different file system structures that define where the information is going to be stored for each file and how each file is going to be accessed and used. And it's up to the operating system to load on support. To read, write, to find, and to use these files. And as a recent example, in the old days there wasn't very much communication going on between, let's say, the Mac and the Windows systems. OS X didn't really read Windows files and vice versa. Now actually both operating systems have support for each other, which makes it more makes files more cross-platform compatible. You can actually get Microsoft Word for the Mac, you can get it for the PC, for the Windows system. So, and the files themselves are identical in terms of their format. And it's the file system that's being read by the operating system, and it's the operating system support as well as the application support that's making this happen. In terms of operations that are provided on files, a file is an abstract data type. It can be defined in operations such as to create a file, write a file, read a file, seek, delete, truncate, open file, close file, all sorts of different low-level system calls to work with files. You see this in a Linux or Unix system when you write code to, let's say, open a file or to close a file. Open a file, read the bytes out line by line or byte by byte, do something with it. And in that example I just gave you, it would be the kernel operating system support that gives you the low-level system calls to open and close, to read, to write, all sorts of different utilities. So you might think that the operating system is sort of the gatekeeper to the file system. It loads the file system support, and it provides the ability, hold on a second, oh, there we go, the lights went off on us. It provides the ability to manipulate the file system directly from the operating system and not from a separate utility or something. Here are some file types and some names with some extensions on them. Executable files in a Windows system or exe, com, bin as an example. The function might be machine language programs themselves. Object code might be precompiled code but not linked. Source code, batch files, text files. And it's kind of interesting when you can tell Windows programmers easily when they create an executable file and they put a .exe extension on there. And because the runtime environment operates on a file name as the file type association, so the .exe tells the file that it's an executable file, which is kind of interesting. Or .com is an executable file, or .dll is a dynamically linked library file. Not the case in a Linux or Unix environment, because the files themselves aren't identifying themselves as what they are. Instead, the content of the file is, and its inode information is identifying it as what it is. So in a Linux Unix environment, the classic executable file actually, it's going to be like, a.out or something, which is an output essentially, which can be called anything, doesn't even need a file extension. And when you run it, it's going to run just like any other executable file, given its properties are read, write, and execute, or just execute, which is needed. So the file extensions themselves have different meanings depending upon the operating system support for the file system and what file systems are actually being identified. Outside of the file system, we have the directory structure. Directories hold files. As a common user, you're familiar with a lot of this stuff from a user perspective. But these are some of the things you need to implement if you're writing your own operating system. You have to actually implement this support. So as an example, for the directory structure and the number of files on the system, it can be extendable. Might have break file systems into partitions, perhaps, treated as separate storage devices, hold information about the files within those partitions. That's a Windows kind of thing. So Windows, if you load on as an example, you load on a USB drive, a thumb drive in your computer, you'll get a new drive letter. It'll have a new partition on it, and it'll be separated. It'll be G or H or I, depending upon what other drives you have on your system. If you mounted that USB drive on a Linux or Unix system, it doesn't actually get its own drive letter, it doesn't become its own partition. Instead, the contents of the USB drive gets mounted and inserted into the directory structure that already exists. And so you go to, let's say for example, /mount/USB or something, and you access the contents of the drive through the directories system. So it's kind of a contrast between how it works in Windows and how it works in other operating systems, Linux-based systems. So in terms of our device directories, that is a collection of nodes containing information about all the files on a partition. We have both directory structure and files that reside on the disk, and we have backups of these structures that are kept on tape in the old days. Actually now the backups are normally kept on CD-ROMs or actually big companies still use tape drives. Actually they're huge expensive drives with big tapes because if it's not broken, don't fix it. But traditionally nowadays things are being either backed up on other servers off-site, or we're looking at CD-ROMs or DVDs that are used as a backup medium. So in terms of the information that's related to the device directory, we could have the file name, the file type, address, location, all this information that you're looking at on the slide here, and the owner as well. In terms of the protection information. Also on a per file basis or per process basis, we might have the current position, the read-write position, maybe usage counts or the amount of bytes that are being read or something. So this is all information that would be in a directory, in a device directory or device structure. And it's kind of interesting as well to consider that in some operating systems we have devices that end up becoming directories or device directory entries or file entries, and then on other operating systems we have the device separated out of the file system concept. As an example, in a Linux system, if we had a floppy drive, if we had a USB drive, it actually gets loaded as a device, FD0 or HD0, HD1 would be hard disk 1, hard disk 0, floppy disk 0. They would have device numbers associated with it. Device numbers would end up getting into entries into the directory structure, and we access the device through the file system, through file pointers, which is kind of interesting because we don't have that as a concept in Windows. In Windows, what we have are devices, and devices get loaded on with device drivers. And they get seen as a separate abstraction, or they get seen as a separate drive letter or something. We don't actually read and write to them via the file system. It's kind of an external concept to that. So operations that can be performed on directories themselves, we can search a file, create a file, delete a file, list a directory, rename a file, traverse the file system. Those are common operations that you're familiar with as a user of most of these file systems. In terms of the logical directory organization, there's a couple of goals to it, because somebody has to decide essentially how we're going to organize this information. How are we going to present it to the users? What kind of tools are we going to give the users to manipulate these files and directories? Well, one of the most obvious characteristics is efficiency. It must be quick in locating files themselves, and must be easy to use, but it must also be quick and efficient. Naming might also be convenient to users. So two users can have the same name, let's say example for different files, and the same file may have several different names associated with it. It may also be nice to have some grouping. It's a logical grouping of files by properties, all Pascal programs, all other games. And the grouping actually comes through with file associations through file types. In a Windows system, the grouping might be associated with all .doc files, and all .ppt files end up becoming My Documents, and they get grouped together in terms of Microsoft compatible file formats. In a Linux or a Unix system, we're looking at more along the lines of grouping through property rights. So we can assign certain files to certain groups of users, and the groups of users would have access to them. So only people who had access to those particular files would actually see the files, and other people who did not have access to it per group or per maybe directory location or per mapping might not necessarily even be aware that those files actually even exist. So Outside of the structure of the directory, the most important kind of concept is the hierarchy that comes out of it. And the hierarchical abstraction is kind of interesting because it does vary among different operating systems. And as a user, you know this because you've been making directories, hopefully. And then you've been making subdirectories and subdirectories. So at a single level directory structure, we have a single directory for all users. All users log in and they see C:\/ or something. Or they see root, or they see one base directory. Naming problems and grouping problems exist in this structure because it's hard to have more than one name for a file or one file with multiple same names per user. So one user couldn't have the same name in the same directory. So that would cause a problem. And as the number of files increase, it's difficult to remember the unique names that have been assigned. And as the number of users increase, users must have unique names for everything. So a single level directory structure doesn't really work too well. And it was kind of the antiquated kind of way of working with stuff. Actually, it is still being implemented. As an example, your thumb drives are single level directories. I mean, unless you load up a bunch of directories on it, the mount place usually gets put into a single directory entry or single level. Yeah. Usually in a Windows system it would be a drive level, so which would give you the directory main directory level or root access. We can take that a bit further and go with a two-level directory structure. So it involves introducing the removing of the naming problem between users, and this is kind of like what Unix and Linux kind of follows through. Each user has a two-level directory called home, and in home, well, we actually have multiple levels passed to because we could have root, then we have home, which is off of root, and then out of home we have all of the different users, B. Hacker and Joe Smith, and everybody else would have their own directory off of that. So the first level contains a list of user directories. The second level contains user files. And you need to specify the path name, and you can specify file names for different users. So you can have home B. Hacker, home J. Smith, home other directories themselves. So system files are kept in separate directories or level 1, which might be efficient for searching. So was there a question back there? No, we're good? Okay. Two-level directories. In terms of our structure, we have a master file directory on the top, and then we have directory number 1, directory number 2, directory number 3, and inside the directories we have files. So, and this kind of seems kind of basic, but what this is doing is essentially giving you the overview of what you've been using for years as a user. But there are definitely some different implementations of it that you may not be familiar with. As an example, the tree structured directories. Linux actually uses a tree structured directory, where we have the root, and then we have subdirectories off of the root, and then we have files or subdirectories that are off of the subdirectories, and then you can kind of think of this sort of like a tree, and these are the leaves. The files end up being the leaves on the bottom of the tree, and these are the nodes that come off, and the nodes are the directories, and we can traverse through the directory structure through subdirectories to get to each one of the different nodes, so that we can essentially find the file that we're looking for. In terms of the tree structure directories, there might be an arbitrary depth of directories of certain length that we can go to. Leaf nodes are files, interior nodes are directories, as I mentioned before. It's very efficient for searching. We can put together a binary search tree for this and actually create a pretty efficient structure for looking for information, because it doesn't mean anything to create the directory structure if we can't search it. And it might also give us some grouping capabilities, and some of the current directory or working directory information might be available to us. As an example, going to spell, mail, program, or typing in type list or something. So MS-DOS uses a tree structured directory. So does, in theory, so does the Linux and Unix system, although the information is kept a little bit differently. In the MS-DOS environment, we also have the absolute and relative path name, same thing we have in a Unix environment, absolute from the root. So the absolute directory is absolute from the root. The relative paths are from the current directory. or from the current working point where we can change directories and manipulate the file system given a relative position. So creating a new file is done in the current directory. Creating your subdirectory is done in the current directory. As an example, make directory, and this is a Linux command actually, not a MS-DOS one, with a directory name. We delete a file by saying rm, file name. I think it's remove or something. It might be rm in DOS, I can't remember. To delete the deletion of a directory, option number 1, only delete its directory if it's empty, or delete all the files and the subdirectories underneath the directory. Remove all recursively, so the -R in a Linux Unix environment does things recursively for us. And then we have the graph directory structures, as in depicted here, which is slightly different from the tree structure, where we have the ability to go from a directory structure to a directory structure to a file. And the file is actually shared by two separate directory structures. This is more, although similar to a tree structure, very similar to what we get in a Linux Unix environment. We have a mapping. So part of your login is a directory structure that's mapped for you. You have access to the same files. In this particular example, we have a file that's being shared by, has two different names essentially, that's pointing to the same file by, let's say, two different users from two different subdirectories off of root. And so we can basically map the file system per user, allow users their own space, and then allow users shared space to files, and then make it so that the user has read access but doesn't have write, or has execute access but doesn't have write or something, or doesn't have read or something. Anyway, so to the directories and also to the files, we can change the properties. So we can essentially map the same files to multiple different users with a different abstraction. And then each user has their own version of the particular mapping or the particular file system. So they allow sharing, as I mentioned. It's implemented by links. In fact, this is one of the differences as well. Thinking about links, we have symbolic links in Linux and Unix that we don't have in Windows. In Windows, we can rename a file because we're working with tree structures. We can copy the file from one location to another. We can copy it to another file name. We can rename the file. But we really only have one of that file. In a graph kind of environment, we can create what's called a symbolic link. Symbolic link is usually for a directory and a bunch of files inside of it. We create multiple ways of getting to the same directory. So instead of making a copy of it, we're creating multiple accesses to it. When we do that, we kind of create a more efficient environment. And instead of, wasting the hard disk space by making copies of everything, we essentially create a link. So we can use the link as another way of accessing it. We can also, use symbolic information and remove it so it's not set in stone. So in terms of the implementation by links, the links are pointers to the other files or the subdirectories, and symbolic links are relative path names. So we have a directory entry that is marked as a link, and the name of the real file the directory is given. And we need to resolve the link to locate the file. So we follow links to go to the file system to actually find the files and the directories that we're interested in getting at. So in terms of the implementation by shared files, we have duplicate information in shared directories. The original and the copy is indistinguishable. We don't know which one is the original or which one is the copy. And we need to maintain consistency if one of them is modified. So, in terms of naming, the naming of the file itself may have multiple absolute file names or path names associated with it, and two different names for the same file might also exist in terms of the implementation. And these are all decisions that you have to come up with when you decide you're going to make your own file system. What kind of structure you're going to put together, a tree or a graph, and how you're going to do the naming. There's pros and cons to both, actually. Most people would think that the tree structure would be more efficient versus the graph. And the graph structure itself is more usable yet harder to work with. So in terms of traversal, you have to decide how you're going to traverse the file system, ensure that the shared data structures are traversed only once. In terms of deletion, removing files from someone who deletes it may leave a dangling pointer, a dangling leak. So same problems you have with using pointers actually in C or C++. If you remove the file and people have symbolic links to it, then you're going to end up with a situation where you go follow the file, but it's not really there. Somebody removed it. They removed it through a different link. So you can preserve the file until all of the references to it are deleted. So you put checks in the file system to make sure that nothing is deleted until, all the symbolic links are removed, which actually ends up happening in a Linux or Unix environment. So if you try to delete something and there's links created that are also accessing it, then you're going to get an error message and the operation's not going to work. So you can keep a list of all references to a file. You can keep track of the number of references using a reference count technique. When the count is 0, then the file can be deleted. Or you can implement your own technique, depending upon how you would like to implement the file system. So here's a general graph of the directories themselves. And now we can end up with a situation here where we have a recursive. This is a recursive directory, by the way, because this directory is actually this directory, which is this directory. And so we can end up with loops in the file system. And these things would be causing problems, actually, because depending upon how you've got the graph structure created, it's going to give you difficulties in terms of, or actually it's going to lead to problematic situations in terms of traversing it, because you still got to traverse it or to read it. So, and as I mentioned before, I called this recursive. It's really a cyclical in terms of its implementation. So how do you guarantee that no cycles in the tree structure are going to exist? Well, you can allow only links to files, not subdirectories. So you set up rules in the file system, and every time a new link is added, you use a cycle, maybe a cycle detection algorithm to determine whether it's okay or not. So if the links to the directories are allowed, we have a simple graph structure that can be created. So there might be a need to ensure that the components are not traversed twice, both for correctness and for performance. And in terms of correctness, this is correct. However, for performance-wise, we're going to end up with a cycle. We're never actually going to find what we're looking for if we keep having to go directory to directory, and the directory never ends. So we have to make sure we at least get out to a leaf eventually. And so in terms of file deletion, reference count can be a non-zero number. So we need garbage collection mechanism to determine if the file can actually be deleted. So in terms of access method, these are things that you have to think about if you're implementing your own file system. How are we going to access the file by the bytes? How are we going to read it in? We have sequential, direct, random, all sorts of different access methods. You get this, are you familiar with this? When you start programming with file I/O, opening a file, reading the file, and then you're going to open it, you're going to read it with an access method. And the access method is going to be, sequential, or it's going to be random, or it's going to be some sort of a predefined setting or parameter that you're going to give the function call. Sequential reads the next, writes the next, resets, no read after the last write, so it goes one by one. Direct is n equals the relative block number. We just go to a block number and we read it. And we read it until all the blocks are done, and then we've done reading the file. In terms of file protection, we have file owner or creator should be in control of the file by theory. In fact, Windows is sort of like this as well. If you created the file, then it's your file. However, somebody else can go into the system, log in as a different user, and still access the file. File protection in a Windows system, not quite as strong as it is in a Linux or a Unix system. In a Linux or Unix system, we have file attributes that we're setting on the files that can restrict it to certain people or to certain groups. And then we have read, write, and execute that can be set. In a Windows, it's an all or nothing. It's either you have access to the file or you don't. There are some file access methods that you can set in the Properties window. You can make it a hidden file, a system file, a read-only file. There are some certain flags that you can set on it, but the level of sophistication is close but not really identical to what you get in a Linux or Unix environment. You definitely have more control in a Linux or Unix. File owner, creator, whoever has control, what can be done, by whom. So the owner is going to tell what other people can do to it. Different types of access: read, write, execute, append, delete, list. These may not necessarily all be supported in every single file system out there, but this is a kind of an example of what file systems do support. In terms of access lists and groups, these are associated with each one of the files or directories with what's called an access list. So the problem might be the length of the access list. If it gets too big, a lot of files on the system, it might be a little bit hard to resolve that information. You know, it might make it hard to figure out, you know, after a user requests a file, it might be 10 minutes later, okay, you can have it now. So it's going to slow down performance. So as a solution, you might want to condense the version of the list. Use modes of access, read, write, execute. So there's 3 classes of users in a Linux and Unix environment, which I'll sort of use as a generic example. There's the owner, there's the group, or there's public. Public is all users. And you get this becomes a lot more close to home when you start uploading files to a, let's say, a web server, and you're trying to give public access to your files, and you get this forbidden error message that comes out of your web browser because you didn't set 777 or 770 or something on your file, 7 being the highest level for all users. So the access mode is going to tell you who's going to access and who's not going to access. And there are bits that are set on the file. So in Linux, there's 3 length bits that are used. And the information is actually kept with the file. So when the file is accessed, then the file, you know, the bits are checked, so there's no list that you have to traverse through. Makes it faster, easier lookup. So fields are user, group, and other, which is our 3 categories, and we have our read, write, and execute. That's our R, our W, and our X. So we use a change mod command. You can use numbers. 761 would be fairly, or 777 or 770 would be fairly open, you know, accessible by the group or by the public, I should say, or public access. So in terms of our file system implementation, and I'm kind of going through this kind of quickly because a lot of you guys are familiar with this stuff already from being a user of a computer. It's hard not to use a computer and not be exposed to file systems concepts because that's what you're using the computer for, to access files for most of the time. But how you set the permissions, how you use the permissions, that's all specific for the file system implementation, and by now you should probably be aware that they're not the same for every file system. Windows uses something totally different than Linux, than Mac systems do. Macs are closer to Linux, Unix, but they're still a little bit different. Macs have journaling file systems, which is an index on the file system. Windows has a compressed file system, which is an indexed file system as well, but it's not a journal, it's an index. So it takes the entire file system, creates an index out of it. So when you go look for a file, you search the index. You don't have to actually search through every single file, which is kind of similar for the journal. It works the same way. All of these techniques are implemented to make the file systems a little easier to navigate and also faster, efficient. Because we don't really care outside of reliability, which is kind of interesting because older file systems made errors. You know, if the file name was too long, it truncated it funny, or it lost stuff, or we had lost clusters from improperly implemented file system links and things. Nowadays it's pretty solid. So nowadays our biggest concern is efficiency, especially if we have a big disk, have a big file system. So in terms of the file system implementation, what you're looking at, I have been looking at on the slide, are some of the different varieties. We have the file system structure itself, the allocation methods, the free space management. These are all things that need to be implemented. Directory implementation, efficiency, recovery, performance. In terms of the structure itself, what we're looking at is a logical storage unit with a collection of related information. Hold on one second. Are you the one who emailed me? Check with her back there.
Oh, sure. Thank you.
Thank you. She's the person taking the test. So for the file structure itself, the logical unit with a collection of related information is the definition of what the file structure entails. For the file system that resides on the secondary storage, or the disk, it's used to improve I/O efficiency, I/O transfer between memory and disk that are performed in blocks, and there's a read, write, modify, access for each one of the blocks on the disk. So file system organization is usually in terms of layers, and we have file control block, which is the storage structure consisting of the information about each one of the files. These are basic file system concepts that fall into the category of the structure. In terms of the mounting, this is when we bring the disk or we bring the file structure into the directory structure. So the file system must be mounted before it can be available to process on the system. So we can mount different types of file systems into the same directory structure. If we're working, actually modern day Windows does this as well, but if we're working in a traditional Unix or Linux environment, we just take this for granted, essentially. We load on the file system support, and then we can load in files of different file types. Hold on. Or take it right here. Yeah. So we can load on different types of file system support, then mount different directories of different drives that all have essential entry points into the same structure of all of these different formats. So the OS is given the name of the device and the mount point located within the file structure at which the files are attached. And then the operating system verifies that the device contains a valid file system itself. And then the operating system notes its directory structure and that a file system has been mounted and specifies the mount point. And then essentially the system has access to the file structure that is on the particular device that has been mounted at the particular location. In terms of the allocation of the disk space, this is another consideration that operating systems have to implement. We have low-level access methods that depend upon the disk allocation scheme used to store file data. These schemes might be of three different varieties. Might be of contiguous allocation, linked list allocation, and perhaps blocked allocation. And to go through these kind of, roughly to give you an estimate about how these would be implemented. In terms of the contiguous, putting all the blocks next to each other. Most defrag does this. Puts the blocks next to each other for files. Contiguous allocation is nice because it doesn't take too much time to access the file. So each file access occupies a set of continuous blocks on the disk. It's simple. You only need the starting point of the block and along with the length of the file, and then you have your file. Suits sequential or direct access, fast. Very little head movement on the disk itself. Easy to recover in the event of a system crash. We know where the blocks are. We know what blocks belong to each one of the files. Problem with continuous file allocation, it's wasteful. So if the file doesn't fit, we can't put it in there. We delete a file, leaves a hole. Then we have internal and external fragmentation that goes on. If we allocate a file to the hole and the hole's bigger than the file or smaller than the file, we have issues. So we have to use like a best fit or a first fit. Dynamic storage allocation problem. So it leads to external fragmentation on the disk. And files can't grow. So if we put a file in and we load a file in on next to it, and another one on top of it, next to it, continuously across the disk, we can't open up that file in Microsoft Word and add a couple paragraphs to it. No room for it to grow. So we actually end up having to put padding at the end of it. And if we put padding on it, then we have, again, external fragmentation. Actually, no. It would actually be determined to be external or internal. External is disk space that is outside of the file that's reserved for the usage of that particular file location, but it's not being used. Internal would be space that was allocated for the file but not being used. So you could argue and say it's internal if you call the entire open area the file. So otherwise it's external because it's outside of what's actually being stored for the file. Users tend to overestimate space. It leads to internal fragmentation. So it's internal if it's inside of the space that's being reserved for the file. It's external if it's outside of the file itself. And in terms of mapping from logical to physical, the blocks to be accessed equals the queue plus the starting address. Not too bad. Displacement into the blocks is equal to R in terms of how long it takes. Here we have our file directory system. We have a start and we have a length, start and a length for file number 1, start and length for file number 2, and these are three different. And we've got essential information that we can look up in terms of a lookup table. That is simple contiguous allocation, not very efficient. Leads to a lot of external and internal fragmentation. We have linked allocation, a little bit better. Each file is in a linked list of blocks. And so the blocks themselves may be scattered anywhere on the disk. We just use a bunch of blocks, we pick the blocks and we put it into the file. So most file systems, modern day systems, use a linked allocation structure because it's more efficient. And the name of the file is basically identifying all of the memory addresses that are associated with all of the links. So blocks are scattered everywhere and anywhere on the disk. Each node is in the list can be fixed to a size of physical blocks or a contiguous collection of blocks. And the allocation is needed and then linked together via pointers, and pointers are used to allocate all the blocks together. So the disk space used to store the pointers as a block, let's say, is 512 bytes. The pointer disk address requires 4 bytes, so user sees 508 bytes of data. So the pointer is a list not accessible to the user, but it is a list that's associated with the file name. So a block is a pointer, and then we have data next to it, and we have a pointer and data next to it. Sort of like a linked list, if you're familiar with the concept. And we have a file, and we have address. The address is the linked list, so each one of the blocks knows about the other. Problem we have with linked allocation, however, is, well, it's the same problem we have with linked list. We're only as strong as our weakest link. So one of the blocks gets corrupted, and we end up losing the rest of the file instead of that one block that got corrupted. So it's simple. You need only starting address. We have free space management, so it's space efficient, no fragmentation. Can grow in the middle, at the ends, no estimation of size is necessary. Suited for sequential access, but not random access, because we have to follow the links from the first block to the rest of the blocks. So it's good for sequential, we just can't do random access on those files. Directory table maps the files into the head of the list for the directory, so the mapping. Here would go a block to be accessed in the Q block, and the linked chain of the blocks representing the file displacement would equal to, into the block would be R plus 1, R plus the next one, R plus the next one. For some of the problems, it's slow. It defies the principle of locality. So talk about moving the arm or the head of the disk all over the place. Now we end up with a situation where we have to go from the beginning of the disk to the end of the disk to the middle of the disk to the end of the disk in sort of a sequential fashion that link all these pieces together. Could be very slow. So the read access is going to be slow. You need to read through the linked list nodes sequentially to find the record of interest. Not very reliable, as I mentioned before. System crashes can scramble files being updated. You lose one link, you've lost half the file. So important variations of linked list methods. The file allocation table, or FAT, basically kept a table of this information instead of using the links themselves, which made it more recoverable. And then we have disk space allocation that's used by MS-DOS and OS2, which, well, FAT is used in both MS-DOS and OS2. Which is linked, it's a linked allocation, but it's held on a table, and the table is at the beginning of the disk. So the table is actually held on the disk as well. Use the table to resolve the links, which makes it more reliable and more recoverable. Outside of the FAT index, we can have an indexed allocation and skip the linked allocation method completely. In an indexed allocation, a pure indexed, it brings all the pointers together into it's called an index block. So we have a logical view. We have an index table with all of the blocks located in it. And here we have a directory, and the directory's got data, and we have an index block. Well, if you're in Linux or Unix, you call these inodes. And now we're looking at a Linux implementation of a linked indexed, which is not, excuse me, an indexed allocation, not a linked allocation, which gives us a little bit quicker access because we're using an index instead of a FAT allocation table, and gives us the flexibility and all the benefits of the linked allocation, but we have an index block. So if the index gets messed up, and then the entire file system is gone, hosed completely, which is not really a good thing. So the weakness is on the index. If you're relying 100% on the index, then the index gets messed up, well then there goes your file system. So you need an index table in order to implement this, and it supports sequential, direct, or index access. So we now, instead of having just sequential access, we can support index and also direct. Dynamic access without any external fragmentation, but has the overhead of the index block. So we have that index we have to load up. So it's a little bit, updating the file system takes longer than reading it because we have to update the index. So same kind of concept you have with databases when you start indexing the tables and then you start updating the table and you start making changes, well, every operation cost spent for the table modification, you have an equal amount of time spent on the indexed allocation. So you just times 2 your efficiency, or minus, divided by 2, and you end up being less efficient. You have 2 things instead of 1 thing to update. So mapping from the logical to the physical in the file are maximum size of 256K words or blocks of 512 words. We need only 1 block of the index table. So we can map it directly in terms of only 1 block. In terms of the mapping from the logical to physical to a file, it's unbound length. So we have a linked scheme, or we have a multi-level indexed in terms of the mapping. So in an index allocation, the linked scheme, the linked blocks of index tables, there's no limit on the size because it can just grow like a linked list, linked index. And then a multi-level index, we have 2 level indexes. To the first level, it's a block points to the set of second level index blocks, which in turn points to the file blocks themselves. We just add another level of abstraction to it, makes it a little bit easier to read. Increases the number of levels based on the maximum file size that's desired, and then the maximum size of the file is bounded. So here's our linked scheme with our index file, where we have an index block that has a link to another link. We essentially nest the links in the links in the index blocks. And here's our 2-level index blocks, where we have an outer index block with 2 sub-indexes inside of it that are eventually linking to files. All this stuff over here is the file linking. This is all the information about the files so we can find them in the directory structure. Here's a combined scheme, which is what Unix uses. So it's a 4K block here where we have combined with the information for the direct blocks of the index. We have the data that's associated with it. We have a single indirect, double indirect, triple indirect, all sorts of different types of direct or indirect, indirect access to the linked index. So in terms of free space management, an important issue might be, how do we find the blocks that we're going to use? So we could keep a list of the free blocks. This is kind of like memory management in terms of virtual memory, we've talked about already. Or we can have the blocks self-identifiable, mark the blocks free, set a bit on the blocks. So we have a bit vector, maybe. So we have a bitmap of free blocks that might exist. Easy to use for continuous files. An example might be the BSD file system uses this actually. So it keeps track of how many blocks are actually not being used or how many free. In terms of a linked list, we have a free list. So in a structure that's using a free list, keeps a linked list of the free blocks, makes them available. You can't get continuous space easily. Not very efficient because a linked list needs traversal. You have to look through each link itself has to follow sequentially from the beginning to the end. And there's no waste of space, however, if we keep a linked list for the free list. We have a linked list of indices or groupings. So we keep a list index of the index block. So each index contains addresses of free blocks and a pointer to the next index block. So we group them together. So you can find a large number of free blocks continuously, group them together in some sort of a designated size, and then allocate them. Or we could use a counting technique. In terms of the counting, we have a linked list of contiguous free blocks that are free. The free list contains a pointer and a number of free blocks starting with that address, and say, at this point we have 3 blocks. At that point we have 12 blocks. So we can tell how big the free space is. In terms of the need to protect, that comes out of the file system protection. It's another operating system kind of concept. It's actually protection itself is an operating system concept. That's where we get the login, the logout, the user management stuff. But in terms of the protection itself, we can have a pointer to the free list to protect that. The bitmap itself must be kept on the disk. Copy in memory may be on the disk. We can set a bitmap essentially to set bits on or off that are associated with it to protect it, so that it's not going to be used, to say that this is going to be used, this is not going to be used, so that it can be shared with other programs or other utilities that might be looking for free space. In terms of the directory implementation, linear lists of file names with pointers to the data blocks. Simple to program if we use a linear list. Time consuming to execute, obviously. Linear search is to find the entry. Not very efficient from an algorithm perspective on searching and sorting. Sorted the list helps and allows for a binary search and decreases the search time. We could have a hash table, which is a linear list with a hash data structure to implement it. Decreases the directory search time if we use a hash structure instead of a list. We might have some collisions, which might be situations where two file names hash to the same location. And this stuff actually happens occasionally. This is when you start having really weird issues with your hard drive. You have, the file thinks it's open, but it's not open. The file doesn't close, or something weird happens. You open up one file and it messes up another file. Each hash entry can be a linked list. Resolves the collision itself by adding a new entry into the list. So efficiency and performance. The last kind of concept that's associated with directory structures. In terms of efficiency, well, that's going to depend on the disk allocation and the directory algorithms. So how are you going to allocate things on the disk and how are you going to find them? So, which is kind of the main problem with each file system in terms of its implementation. The types of data that's kept in the file directory and the directory entry leads to the efficiency as well, and the dynamic allocation of kernel structures may also lead to efficiency. Performance might be improved by onboard cache for disk controllers, creating buffers. Disk cache itself, a separated section from main memory for frequently used blocks, block replacement mechanisms for least recently used, or free behind or free ahead, which moves blocks from the buffer as soon as the next block is requested. So if you can cache some of that information instead of having to read and write back and forth to the disk, if you cache it ahead of time, it might improve the efficiency in terms of the performance. So improve PC performance by dedicating sections of memory as virtual disk or RAM disk as well, which might come in handy. In terms of recovery, well, we're all familiar with that if we back up our hard drives. So it ensures that the system failure does not result in loss of data or data inconsistency. We can build recovery into the operating system, which would be a Linux and a Unix thing with FSCK to fix the file structure. Might be a FDIT, well, that's a formatted disk in DOS. We don't really have an FSCK equivalent in DOS these days, but the file system itself runs consistency checks constantly, defrags itself. Nowadays with all this automation that we have in the operating systems in Windows. So a consistency checker might run in the background, compares data in the directory structure with data blocks on the disk, tries to fix those inconsistencies when they exist. In terms of a backup, we might use the system programs to back up the data to another storage device. We don't really have magnetic tapes, but we don't have floppy disks anymore either. It's kind of an also. Replace those two words with CDs and DVDs probably, or USB drives. So, of course, USB drives aren't really as big as hard drives yet. So, and in terms of restore, that's where we're going to recover those lost files in the disk by restoring it from a backup. So, that was everything you ever wanted to know about file system support and file system concepts. And that concludes our look at file directories, file systems, and all those nifty little easy concepts when it comes to operating systems, because these particular concepts are used by users every day. So it's not something new. It's not something that you're not familiar with. So questions, comments, or concerns? Nope. Good. We're done for today. See you next week.